My name is Timur Doumler, also known as Timur Audio on Twitter. I am a developer advocate at JetBrains. We make developer tools such as the C-Line IDE or ReSharp or C++. And today I'm going to talk to you about lambdas. And I'm going to try to do kind of two things in this talk. One, talk a little bit about how lambdas actually work under the hood and how that evolved over the course of the different C++ standards. And the other thing that I want to do is I want to talk about certain patterns or idioms where I saw people programming with lambdas, and I saw people using certain techniques with lambdas, and I want to show you some of those. And some of them are like really, really useful things that I think every C++ developer should know. Others are maybe more of a curiosity, something that is kind of weird, teaches us something about the language, maybe not something you should use in production code. So it kind of depends. The idioms are kind of different, as you'll see. And my goal, my very ambitious goal for today is that everyone here in this room, no matter if you're a beginner or even if you're like an expert or you're on the committee or something like that, you should learn at least one thing about lambdas in C++ that you didn't know before. So this is kind of my very ambitious goal. Let's see if we achieve that. So lambdas we have in C++ since C++ 11, so that's quite a while ago. Let's say we have some simple example here. We have some struct person, and then we have a vector of people, and then we're going to do some standard algorithm on this vector, for example, sort. And a lot of these algorithms, they take functions as predicates, and they take them as arguments, right? And so before C++ 11, if you wanted to pass a function to another function that takes a function, such as sort, we had to either pass row function pointers, or we had to make a struct with an operator paren, or there were other kind of macro-based solutions like boost lambda, if anybody of you remembers that. Since C++ 11, we have Lambda Expressions, which are these things starting with square brackets. And I'm not going to start completely from zero. I'm going to assume that you have some knowledge of Lambda Expressions. So I'm not going to explain everything from scratch, like what these square brackets mean. I'm kind of assuming that you already know that. So that's a Lambda expression. The standard, the C++ standard, actually spells out quite precisely what happens when you write a Lambda expression. So when you write a Lambda expression, the first thing that the compiler is going to do is going to generate a so-called closure type, which is a class type that has a public inline function call operator. Okay. So this is kind of at the top is the code that you wrote, and at the bottom is some approximation of what the compiler generates under the hood. So you write a Lambda expression, and then what the compiler generates is this closure type. And the name of that closure type is some type name that you cannot name. It's something that the compiler generates. So I wrote __ lambda something something. In practice, it's going to be probably even longer than that. Maybe it's going to contain the file name or something like that. So it's going to be a long kind of compiler internal type name that you cannot name yourself. So it generates that closure type with an inline call operator. And the body of that call operator is going to be exactly the body of the Lambda expression that you wrote. And then the second thing that the compiler is going to do is going to generate an unnamed temporary instance of this closure type. And then that instance is your Lambda object, and then you can do with it what you want. A few things that are important here. This inline call operator is actually const by default. So this is one of the cases where C++ got the defaults right. It's const by default, so you cannot modify members there. If you do, you have to write mutable. If you don't write mutable, it's const by default. The other thing that is interesting is that the return type is going to be deduced for you by the compiler. So in this case, it's bool. However, you can also specify the return type explicitly with this trailing return type syntax. It's not no except by default. If you want the call operator to be no except, you have to write no except. And yeah, thus you get this. And so there are a few other things going on here. The compiler is also in C++ 11 going to delete the default constructor and delete the assignment operator. So in C++ 11, and we're going to see later that in C++ 20 it's different, but in C++ 11, lambdas are not default constructible and not assignable, which means that the only instance you're going to get, the only instance of the closure type you're going to get is the instance that the compiler generated for you. So the other interesting thing is that lambdas that do not capture anything, lambdas that do not have a state, so lambdas where the square brackets are empty, have an implicit conversion to function pointer. So implicitly convertible to raw function pointer. So if you have some kind of legacy call here, like C APIs do that very often. They take a raw function pointer and then you give that a lambda expression. As long as the square brackets are empty, that's just going to work. Okay, you're going to get an implicit conversion to function pointer. And again, the standard spells out what actually happens here. It says, well, the compiler is going to generate a conversion function to pointer to function. And it looks something like this. Again, this is some approximation of the code that the compiler actually generates. So this underscore underscore func type is the type of a function pointer which matches the signature of the lambda that you wrote. Then you're going to get an operator, a conversion operator to this type. Okay, so this is the implicit kind of inline conversion operator to function pointer that you get. And now that we know that, we come to the first Lambda India today, which is the Unary plus trick. And that's one of those where I would say this is kind of an evil hack. Like, do not do this in production code. It's kind of really interesting. It teaches us something about how lambdas work. But it's kind of more of a curiosity. So I wouldn't necessarily use that in production code. But I think it's kind of cool. So we already said that lambdas implicitly convert to function pointer. But what if we want to do an explicit conversion to function pointer? In other words, what if we have something like this? So we have a raw pointer type, and we initialize it with a lambda expression. Is this going to compile? Who thinks it will? Who thinks it won't? OK, you're right. You get an error. You cannot deduce this type here. Because you do not have this, like that just doesn't work. And so how do we can make this work? Well, we can explicitly cast it, right? So we can write this long static cast to pointer to function, which is a bit long. Turns out, we can also just write it like that. And that's going to compile, and that's going to do the thing. What's going on here? So this is kind of cool. So the unary plus operator is obviously not defined for lambdas, right? It's not something that is part of this closure type that the compiler generates for you. However, the unary plus operator is defined for pointers, including pointers to function. So if the compiler sees the unary plus operator, it says, OK, well, that only works for pointers. Therefore, I'm going to implicitly convert this to a pointer. So your lambda is going to be implicitly converted to a function pointer, and then the unary plus operator is going to be applied to that function pointer. And what does the unary plus operator do when applied to a pointer? Nothing, exactly. So all it does is it's going to static cast the lambda to a pointer, which is kind of cool. Please don't do this in production code, but I think it's interesting. So we talked about captureless lambdas. So all of the stuff with the function pointer conversion only works for captureless lambdas. Let's talk about captures. So captures is when you capture a variable from the scope where the lambda expression is in. So it means your lambda now has state. Again, I'm not going to explain like from scratch how this works. I'm going to assume that you have some basic knowledge of that. So you can catch entities by value. You can capture them by reference. You can capture them explicitly. You can do some kind of mixture. What does the compiler do under the hood? So again, this is some approximation of what you get when you write this. If you here, for example, capture these two variables, I and j, by value, what the compiler is going to do is going to add two private members, non-static data members, to your closure type. And it's going to initialize those data members with the values of the variables that you have captured. Okay? So this is kind of what this code does. And again, the standard spells out pretty precisely what's happening here. It says that for each entity captured by copy, you get a non-static data member. However, they don't have names, and the order of them is unspecified. So if you go back to, this slide, this is why I wrote int __ I for the members, because it's some kind of compiler internal name again, so you cannot name them. You cannot say lambda.I. The only way you can refer to these members is by referring to the variable that you captured with that name. So you write I, and what you actually get is you get an access to this data member that the compiler generated for you. When you capture by reference, something very similar happens. You get private members that are references notionally. And again, these references are going to be initialized with the values of the variables that you've captured at the point where you write the Lambda expression. However, here, the standard says that the compiler has even more freedom. It is actually unspecified whether it even adds any extra members if you capture by reference and how many of them there are. And the reason that this is so flexible here is to give the compiler more opportunities for optimization. So for example, if you capture 2 variables by reference, but you only ever use one at a time, you use one and then later use the other, it can reuse the same pointer. Or for example, if the variables are close to each other, it can, instead of storing 2 pointers, it can store 1 pointer and then use like an offset or something like this. So this is to enable optimization opportunities, basically. And again, the call operator is const by default unless you write mutable, which means if you capture something by value, you cannot modify the value of these captured variables inside the Lambda. If you capture by reference, you can. If you capture by value, you cannot, because they're going to become members of the Lambda, and you cannot modify members in a member function that's declared const. So hopefully that's not surprising. The other thing you can do is you can capture this. And if you capture this, then you get to call members and member functions of that object that you're in. So you can have a Lambda inside a member function of a class and just naturally refer to other members of that class inside that Lambda. What happens under the hood is it actually captures the this pointer. So this is actually really important. If you then refer to the I here on the left-hand side inside the Lambda, it's not going to actually capture the I because it's a member. And you wrote capture this. So what it's going to capture is only going to capture the this pointer. And then if you access the member inside the Lambda, it's going to access it through this pointer that you captured. And so this is a bit of a dangerous kind of thing because the rules, how this actually happens, you can also capture this by value or by reference, and there's some nuances there. And the rules for that actually have changed also throughout the different versions of the standard. So it's a bit more complex, like the rules around capturing this correctly. So I'm not going to go into detail here, but if you run into problems with this, you can go to CPP reference, you can look it up. So hopefully you're going to be fine. So instead of talking about capturing this, let's talk about some other interesting things that can happen with captures. So one really, really important thing is that you can only capture local variables. If something is not a local variable, you cannot capture it. For example, here you have a static object. And even though it's inside some scope, so it's not going to be visible everywhere, but it has static storage duration. So it means it is not a local variable, it's a static variable. And that means you don't get to capture it in a Lambda. It's not being captured, it's just being accessed. So that means if you write it like this, you might think that you're capturing the I by value and that you're copying it, and therefore that if you modify it inside the Lambda, you're not modifying the I outside. But actually, you are. So what is this program going to do? What is this going to return? 43, exactly. So you think you're capturing it by value and making a copy, but you're actually not, because it's not a local variable. So you're actually modifying the outer I when you do ++I inside the Lambda. And actually, you don't have to write any capture at all, because you're not capturing anything. You can just leave this empty, and it's going to still work, and it's going to still do the same thing. And it's the same as for static objects. It's also the same for global variables, which I hope you don't have in your code. So if you have a global variable, it's the same thing. You're not actually capturing it. You're just accessing it, right? So again, the square brackets can be empty. You can still do ++I in there, and that's going to modify the global variable. Now, something that's a little bit more subtle, you also don't capture variables, even if they're local, if the Lambda doesn't ODR use them. Okay, so you only capture things that are ODR used inside the Lambda. And ODR use is kind of a term from the standard. You can, again, look it up, what it means exactly. But here's an interesting case. You have a constexpr variable. So we have a variable, the value of which is known at compile time. And so then if you use this value, it's essentially a compile time constant. And if you use this value inside the Lambda, that is not an ODR use of the variable. That means you don't have to capture I. So again, the capture here is empty, but you can use I, you can print it from within the Lambda, it's fine. You don't have to capture it, it's just there. Because that's not an ODR use, because it's not in compile time. However, if you want to take the address of that variable, that is an ODR use. So then it's not going to compile unless you explicitly capture it. And it gets even more subtle, because even if you don't write constexpr, if you have a const variable of integer type, const variables of integer type are implicitly constexpr. So that means if you have a const int here, or const size t or something, that is implicitly constexpr. And again, if you use the value of that variable, that is not an ODR use. Therefore, you don't have to capture it. However, if you have a const float, a float is not an integer type. And therefore, this logic doesn't apply. It's not constexpr. You must capture it if you want to use it inside the Lambda. OK, so that's a bit interesting there. The rules are quite subtle. It's worth knowing. And now we come to the second idiom, which is called immediately invoked functions expressions, or some people also call it immediately invoked lambdas. And that one, unlike the first one, is actually something that I think has been around for a while already and is very, very popular. And this is one of those idioms that I think really everybody should know, because it's so useful and it's really good practice. And I think it can be useful in many situations. What does it mean to immediately invoke a lambda? Well, we have heard what a lambda actually is when you write a lambda expression, what the compiler actually does with that. We don't necessarily have to assign that to a variable, right? We can do whatever we want with that. So if we have a lambda expression here, we can also instead just call it right there, right? So what's going to happen here, it's going to create the closure type. Then it's going to create a temporary instance of that closure type. And then we wrote paren, so it's going to call that temporary instance, which is going to execute the body. And then, because it's a temporary, we didn't assign it to a named variable, it's just going to do poof and go out of scope, and then that's it. So basically, this is just a weird way of writing hello world. This will just print hello world, right? So you might think, this isn't really useful, but actually it really, really is. There is a particular use case where these immediately invoked lambdas are super, super useful. And it's when we initialize objects, and the initialization of the object is a bit more complex. So we don't just assign a value, but we have to run some code, maybe some branches in there that depend on some other stuff. And we need to do all this to initialize the variable, in this case, foo. So we need to check if we have a database, and then depending on that, like, we're going to assign a different value to it. You can write it like this. It's not great, right? Because it's this kind of two-step initialization where we declare the variable, we don't assign anything to it, so potentially you're going to have uninitialized variables in there, you're going to maybe have undefined behavior if you access that kind of in between. And then in the second step, we kind of initialize it by assigning a value to it, right? So we're kind of splitting the initialization into two steps, which is usually not safe and not good practice. Now, in Java, for example, this problem doesn't exist because in Java, oh, actually, no, I come to Java in a minute. So one problem is that this isn't great, the two-step initialization. Another problem is that it might not actually work because foo might not have a default constructor. And if foo doesn't have a default constructor, this is not going to compile. And the third case where this is a problem is if foo is const. And now I come to Java. So in Java, instead of the const keyword, we have the final keyword. And the final keyword says you can only assign to this object once. Right? So in Java, this would compile because we just assign to it once. It's fine. We cannot modify it again. But in C++, the const keyword means something else. The const keyword means you only get to initialize it once, and it has to be at the point where you declare it. right? So now we have a problem because we have to write const foo and then initialize it right there in that statement, but we have this potentially long block of code which is doing the initialization. How are we going to do this? So, without lambdas, there are a few things you can do which are not great. One of them, if it's simple enough, you can maybe write ternary expressions like this, right? But if the code is a little bit more complicated, you have like nested branches, it's going to get really, really ugly and unreadable really, really quickly, as you can probably imagine. The other thing you could do is you could kind of extract the initialization code into a function and then kind of call that function and assign the return value of that function, right? So that works, but now you're kind of splitting the logic, right? So you have the object here and then the code that initializes it kind of there in a separate function, potentially somewhere completely different. It's going to make it hard to reason about your code because it's not local anymore. And then if the initialization depends on local variables, you now have to pass these local variables as a parameter to the function. So it all just gets messy. And so here, lambdas are actually really great because what you can now do is you can say, OK, const foo equals, and then you write a lambda that just does all the initialization, returns the value, and then you can immediately call the lambda. So note that at the end I wrote paren, which immediately calls the lambda, and it's going to just assign the return value of that lambda to the object. And that solves the problem. And so it's not only great for just initializing one object, it's also great for everything that uses perfect forwarding, like emplace back, make shared, make unique, all of that stuff. So here, we have a vector of these foos, and we can just make a new one with emplace back, and just instead of putting the value there, we put a lambda there and immediately call it, right? And it's going to initialize the new element with the return value of that lambda. Now, some people say this paren at the end, like it's very, very easy to overlook it. So it might look like you're passing a lambda, like in the first slide where I was doing sort, I was passing a function, right? So it looks like you're passing a lambda to emplace back, but you're actually only passing the return value of that lambda. So it might be a bit hard to see what's going on here. So what you can do instead of paren at the end, you can write std_invoke at the beginning. And std_invoke is a function that we had since C++17. And the only thing it does is it takes a function and calls it, right? So basically, it's not doing anything else than the paren in this case, but it is a little bit more visible because it's like right there in the beginning. There's like a few more characters, so it just expresses intent a little bit more. So it kind of depends, I guess, on your coding style. It might make sense to write it like this. And then you can actually do more cool stuff with these immediately invoked lambdas. And here is a case which is, again, a little bit more for curiosity. And this is something that I learned from Daisy Holman, who did a talk, what you can learn from being too cute. And this is one of the tricks that she showed there. And I think it's really cool, so I'm just going to talk about it here. So the task is that you have a snippet of code, and you only want to run it once. Like, for example, here you have some kind of struct x, and you have a constructor. And you want to run this code when you construct an object, but only once, only the first time you initialize one of those, right? And then never again. And this is actually really useful. I actually have this. I have a use case for this in a library that I'm working on where we have a class, and then what the class does depends on whether the CPU of the machine it's running on supports a certain CPU instruction, for example. And that's a runtime check that you have to do. But obviously, you only have to do that only once, right? So you're only going to do this check once when you first use one of those things, and then you never again have to do that. So we have some code, and we want to call it once. And if we create a bunch of these objects, we still want this code to only be called the first time and then never again. How are we going to do this? Well, we can wrap it in a lambda, because lambdas are great. We can then return some value from the lambda, and it's really not important what value that lambda returns. It doesn't really matter. It just needs to be something. And then we immediately invoke that lambda, causing it to call this code and return 0. And then we're going to assign this return value to a static object. OK? And so that is going to do exactly what we want. Well, how does this work? Some of you might be familiar with the Maya singleton, and if you are, then you can probably guess what's going on here. Since C++11, we have this guarantee that if you initialize a static object, it's guaranteed to be initialized exactly once. And so, so this works. And you actually have an even better guarantee. This initialization is also thread safe. So which means you can actually initialize these X objects from multiple threads simultaneously, and you will still only call this code once, and it's going to be thread safe. So the compiler is going to insert invisible locks to make sure it's all thread safe and to make sure that this code is only going to be called once. There is one caveat here, which is if you run this constructor a second time, there will be an implicit check, which is some kind of atomic flag, whether this has already been called yet, in order to make sure that it's not going to be called again. So there's going to be a little bit of a runtime overhead. However, interestingly, Daisy in her talk, when she initially presented this, said that she'd done some benchmarks, and we have actually this in the standard library. So we have a function in the standard library called std call once, which is doing exactly this. However, if you write it by hand like this, apparently it's a lot more performant than the standard library version. I don't know why. It might change, but apparently that's the case today. So I think that's interesting. All right, so we're done with C++11. Let's go to C++14. Excuse me. In C++14, we got a bunch of new features. One of those is generic lambdas. So since C++14, we can write something like this, where we have a lambda, and it takes a parameter, and instead of spelling out the type of the parameter, we just write auto. Okay? And this is really cool, because then the compiler is going to deduce the type for us. In cases like this, where we are iterating over a map, so we are doing something with a standard algorithm on a map, and we have to pass a lambda that takes an element of that map, the element type of that map, of a std map, probably not everybody can immediately write out what that is. Hint, it's not pair of int std string, right? It's something else. So, but you don't have to worry about this. You can just write const auto, and it's just going to work. So what's happening under the hood? If you write a generic lambda and you write auto I, the compiler is going to do something like this. Again, this is an approximation, because we can't look into the compiler. It's not going to tell us, exactly what it does there. But this is kind of an approximation of what it does. It helps to understand what's going on here. So if you write a generic lambda, it creates a call operator, which is now a function template. This is really important, because for a while, when I first heard about generic lambdas, I thought that somehow the lambda is a template now. But that's not true. The lambda is not a template. The call operator of the lambda is a function template. That's a really important distinction. And so that's what the compiler is going to generate for you. And if your lambda has no state, if it doesn't capture anything, like this one, you are still also going to get the implicit conversion to function pointer. But now that conversion operator is also going to be a template. Okay? And that's really cool, which means if you have, again, our legacy call, which expects a raw function pointer, you can give it a generic lambda, and it's going to deduce what type you're trying to do. What you're trying to do. It's going to deduce what instantiation of this template it needs, and it's going to convert that. It's going to figure out that you need the int version, and it's going to convert that to a function pointer. So that's just going to work. However, the other trick with the plus, that is not going to work anymore, because here the compiler literally doesn't know what type you need, what type you're trying to create here, what's the concrete function pointer type. It's not clear, right? So that's not going to work. The other cool thing about generic lambdas is that they support perfect forwarding, right? So if you write auto-ref-ref, that's a forwarding reference. It's becoming clear if you, again, write out kind of what the compiler generates, more or less. It's something like this, where you get a operator paren, which is not a function template. And if you look at this, you see template type t, tref-ref. OK, that's a forwarding reference. So you can perfect forward arguments into it. It also supports variadic templates, so you can have variadic lambdas. That's really, really cool. And because you can now have these auto parameters, it makes it really, really easy to pass lambdas into other lambdas, right? So because you cannot spell out the type of a lambda, but you don't have to because it's like you could just write auto, right? So you can have, if you're into functional programming, you can do all of these really, really fun stuff where you have a lambda and it's going to take a lambda as an argument. It's going to return another lambda which calls the first lambda twice in a row. So this is what this does. And yeah, you can do lots of really, really fun kind of meta programming stuff with this. If you're into functional programming, you can do like higher order functions and higher order functions that take other higher order functions and chain them and do all kinds of fun stuff. And this syntax with the auto makes it really, really easy. So here is another idiom which I'm not sure you're going to need a lot in practice, but I think it's really, really interesting to be aware of this because there might be cases where this comes up, and I think this is a really cool technique. So this is something that I learned from Björn Fahler. We said that if we have a generic lambda, the closure type that the compiler generates, that's not going to be a template. The call operator is going to be a template, right? But what if we could make the lambda itself also a template? Wouldn't that be cool? And so at some point, I was on Twitter. I was actually preparing this talk, and I was asking people, hey, so I learned this really weird thing about lambdas today. Like, what is the weirdest thing that you learned about lambdas? And can you just post that? And then I got this reply from Björn, which I thought was really interesting. He said, you can make a lambda a variable template and access the template parameter in it. And then he just posted this snippet of code there. And when I saw this, I was like, huh. What's going on there? This is interesting. So variable templates is a feature that we had since C++14. So let's try and figure out what's going on here. So we make a variable template, and it has a template parameter t. And then we assign a generic lambda to it, okay? And so now what happens, kind of, conceptually, is that we have now two different types of template parameters, right? So on the one hand, we have the template parameter of the variable, which is the t, right? And that is effectively going to become a template parameter of the lambda itself. So the lambda itself is now kind of a template. And on the other hand, we have this template parameter, which is the generic lambda template parameter. And that's going to be the template parameter of the call operator, but that's a different set of template parameters, right? So now we can kind of separate out like template parameters for the lambda and template parameters for its class. Template parameters for its call operator. And this can be useful in a very, very particular scenario. And I messaged Björn when he posted this, and I was like, this is really cool, but I don't understand what can you do with this? Do you have an example? And he was like, oh yeah, I actually had to use this once. Let me write you a toy example to demonstrate what's going on here. And this is the code that he sent me, and he gave me permission to reproduce this here. So let's say we have some kind of struct which stores a time point, and for some reason we are storing it as a variant, which can store it either as milliseconds or as nanoseconds. And then we have this convert function here, which takes another function. So this is a higher order function. And it takes a conversion function and applies it to the variant using std_visit. So it's going to take the variant and apply this conversion function that it's being passed in to it. Okay? So it's going to convert the internal representation to something else depending on what function you pass in as the converter function. And so the converter function that we're passing in, we're going to pass in std chrono duration cast. And you want to cast this time point to microseconds, which is the US there, right? So we're just passing in a function, and we want that function to be applied to the std_visit in there. is this code going to compile? Who thinks this is going to compile? OK, who thinks it's not going to compile? OK, a few hands. Yes, there is an error. And so what's the error here? And it turns out, well, duration cast actually has 3 template parameters, right? So it has this first one, toDuration, which is the one that you're going to cast to, in our case, microseconds. So that's the one that you write when you write duration cast, angle brackets, something. But then it has 2 more template parameters, this rep and period. And they are being deduced typically, they're being deduced from the argument that you pass in, right? So you can specify all 3, but you don't really do that. You specify the one that you care about, and the other 2 are going to be automatically deduced for you from the argument. But if you go back to this code here, there is no argument here, because we're not calling it, right? We are just passing the function to another function taking a function. And so it turns out that you cannot do this with a function template, right? So what you're passing needs to be some kind of function pointer, effectively, right? Or function object. But if you write a template, a function template is not a function unless you instantiate that template. But you have only specified one of the 3 template parameters here, and the other 2, they can be deduced when you call it, but you don't call it here. It's going to be called somewhere inside visit, and at that point, like, that information just isn't there. So that doesn't work. And so here's where this pattern comes to the rescue. You can wrap the duration cast into a helper struct. And you can basically split the template arguments into 2 categories. Template parameters that we want to explicitly specify when we pass this function somewhere else. And then template parameters that we want to be deduced at the call site, right? And so we say that the first template parameter, the duration, that's the thing, the US there, that's the thing that you want to specify. So that now becomes the template tag name T, right? That's the template parameter of the variable template. That's the one that we specify, this one here. And then the other 2 template parameters, you want them to be deduced where this function is being called. And so those are going to be the template parameters of the call operator of this generic lambda, right? And so that is going to be called somewhere inside the visit. And at that point, they can be deduced right there by the compiler where you call it. So you kind of separate the template parameters that you want to specify yourself and make them the variable template parameters, and template parameters that you want to be deduced from calling the lambda and make them the template parameters of the generic lambda, just by doing the usual generic lambda thing. So it's probably a bit of a convoluted case, but apparently it comes up sometimes. So I think it's really cool to just know that you can do this, that you can make a lambda a variable template. I think it's a really cool technique. All right, let's briefly talk about Init Capture, because that's the other feature that we got in C++14. What's Init Capture? Well, previously we couldn't capture, for example, variables that were move only, like unique pointer, because if you capture something by value, you always copy it. Now we can do this. We can basically initialize a new variable inside the capture and just say equals and give it some value, and now we can still move a unique pointer into that. And the name putter, it can be the same name, it can be a different name, it doesn't really matter. And what happens when you do this, again, at the bottom is some approximation of what the compiler generates. It's going to generate a new private data member for you for every init capture. It's going to deduce the type from the initializer, so it knows in this case it's a unique pointer. And then it's going to initialize that new member with the initializer that you wrote, right? So that's super useful, and there's actually another pattern here, which I got from Bartłomiej Filipek's book, C++ Lambda Story. I highly recommend this book. It goes into way more detail about lambdas than I do here in this talk. It actually starts from 0, so if you really want to understand lambdas like from 0 until like all the details, I recommend this book. You can also buy it as an online book, and he gave me permission again to reproduce this example here from his book, because I think it's kind of demonstrates the technique very well. So what you're doing is you want to use Init Capture for optimization. And so this is the example. It's not really important what exactly is going on here. We have some kind of vector of strings, and then we have another string here, which some string. And then we're capturing that string in the Lambda. And then inside the Lambda, we are modifying that string. Okay? So we're appending something to the string. And because this is a std find if, this is going to have a loop inside. So this addition here, this like concatenation of the prefix and with the other string, that's going to happen every time, like on every iteration of the loop. And that's really inefficient because it's going to, every time it's going to create a new string object there. It's going to potentially do a memory allocation for that. And it's going to do that every time for every loop iteration. But the result is always the same, right? So it's much more efficient to move this operation into the init capture. And so we're going to compute this value only once there, store it in an init capture variable stir, and then we can refer to that stir from inside the Lambda. And this way, we saved a lot of CPU cycles because we can just do this operation once in the init capture. So I think this is a really cool technique that everybody should be aware of because this actually comes up in quite a lot in real code. And now we're already at C++17. Well, in C++17, we again got lots of new features that have to do with lambdas. Lambdas, since C++17, can now be constexpr, which is really cool because now you can execute them at compile time. You can use the result of a lambda as a non-type template parameter, for example. Or you can use them in other types of compile time metaprogramming, which is really cool. And another feature that we also got in C++17 is class template argument deduction, or CTAD. Now, what is CTAD? I'm sure some of you have heard of it, or many of you probably are using it already. We had this in C++17. CTAD means if you have a template like vector, a class template, you don't have to spell out the template parameters of the vector, so you don't have to write vector int. You can just write vector, and then the int is going to be automatically deduced from the initializer. So here, because you wrote an initializer list with integers, the compiler can figure out that this is a vector of integers, and you save a lot of typing. And there's like obviously a lot more complicated examples where this makes a lot of sense, where writing out the template parameters would be very complicated or cumbersome, and this just makes it a lot easier. And so this CTAD feature doesn't really have anything to do with lambdas per se, but it enables another really, really, really cool technique that has been around for a few years now. I've seen it on CPP reference and in a couple other talks. And I think this is also a really, really cool tool to have in your toolbox. And that's the lambda overload set. So what you want to do here is you want to create an object that is a callable object. So you can call it with the usual function call syntax, but it acts as an overload set. So if you give it, for example, an integer, it calls an int overload. If you give it a float, it's going to call a float overload. And we want to give it the different overloads as lambdas, right? So you want to have a set of lambdas, like one for int, one for float. And you want to have one object, and depending on what you call it with, it's going to call the right overload. Make sense? Cool. How are we going to do this? Well, we now know that if you write a lambda expression, the compiler is going to generate a closure type for us. A closure type is a class type. Because it's a class type, we can inherit from it. So you can actually inherit from lambdas. This is really cool. Of course, you cannot just write : lambda type and inherit from it directly like this, because you cannot spell out that lambda type, right? But what you can do is you can write a variadic template, which takes a bunch of template parameters, a bunch of types, and it's going to inherit from all of these types. And then it's going to use the call operator of all of these types. So which means if you write using ts operator paren, ... it means that whatever types we give it, if like the call operators of those types are going to be callable directly through this overload object. So it's kind of inheriting the call operator, so to say. And the other interesting thing about this is that overload is an aggregate, right? Because it has no user-defined constructors. and has no private members or anything like this, which means it's an aggregate, and the elements of that aggregate are the base classes, right? The base classes. And so what we can do is we can initialize an overload object with aggregate initialization using the braces. And you can give it a bunch of lambdas, and those lambdas are going to be the base classes of that overload set, and it's going to inherit the call operator from them, okay? Now, in C++17, to make this work, we also need to write a deduction guide, which is like 2 more lines. But since C++20, we have CTAD for aggregates, so we don't have to do that anymore. Like the compiler is going to do that for us, so this code in C++20 is going to compile as is. And now we can do this. We can take this f, and we can call it with an int argument. It's going to call the int lambda, and we're going to call it with a float argument, and it's going to call the float lambda, okay? And this is really, really, really cool if you use it with std variant. So if you have a std variant of int and float, you can call std visit and pass it the overload object. And then depending on the current state of the variant, if the variant currently holds a float, it's going to call the float lambda, and the variant is going to currently holding an int, it's going to call the int lambda. Okay? So I think this is a really, really, really cool technique, and that one actually does come up quite frequently in real-world code. So I think this is also worth knowing about. And you're also going to see this on CPP reference and in other places. So it's worth kind of knowing how this works if you need to use it. All right, and now we already come to C++20. In C++20, we got a lot more stuff for lambdas. Lambdas can now capture structured bindings. Lambdas can capture parameter packs. Lambdas can now be const eval, which means you can only call it at compile time, right? If you call it with a compile time constant like 5, it's going to be fine. But if you call it with a runtime variable, it's going to error out. And we got templated lambdas. So that means in generic lambdas, it's going to have a templated call operator, but we can't name the type, right? So now in C++20, we can explicitly write these angry brackets, and we explicitly write the template arguments of that call operator. And that's really cool. For example, once you can name t, you can apply constraints on it. You know, you can use requires clauses and all kinds of stuff. You can do some kind of meta programming on the lambda, which is really cool. And then these are 3 other things that we also got in C++20, which are really, really cool. So lambdas are now allowed in unevaluated contexts, such as decal type. And lambdas without captures, so where the square brackets are empty, you can now default construct them and assign them. And remember, in C++11, that was forbidden. Since C++20, that's now allowed. And that lets us do really cool stuff. So previously, before C++20, it was not possible to have a lambda be a data member of a class, because you cannot write this, because you cannot declare a data member with auto. That's not allowed. So, but because you cannot spell out the type of the lambda, there was just no way to make a lambda a member unless you just template it on the type of the member, and then the member can be anything. But since C++20, you can write it like this. Because we can write a lambda in an unevaluated context like decal type, you can just say lambda expression, decal type of that, and now we have a way of naming the type of that lambda. Now we haven't created an object yet, but now we can say that type f, and because it's default constructible, now we're constructing a lambda of that type, okay? So now we have a lambda member, and you might think, okay, why is this useful? This is kind of a bit weird, but actually, this is useful in lots of places. This is kind of all over the standard library. Whenever you have a class that has a class template that has a function as a template parameter, this is super useful. For example, unique pointer. First template parameter is the element type. The second template parameter, which is optional, is the deleter. Previously, we had to pass the deleter explicitly at runtime in the constructor. Now, like, if you want it to be a lambda, right now you can just write the lambda inside the decal type. You say, okay, my deleter is going to be this lambda, and you're going to just bake it into the type of your unique pointer there. And then you can just create those my unique pointer thingies, and all of them will have this deleter, and you don't have to do anything anymore where you declare the variable, because it's kind of baked into the type. Another example is std_set, where the second template parameter is the comparison function, and again, you can say decal type lambda, and that's going to be your comparison function, and you just bake that into the type, and you don't have to worry about that when you declare your variable. You don't have to pass anything in the constructor or anything like that. Now, this is actually interesting. So it turns out that every new lambda expression generates a new closure type. So if you start to program with these decal type lambda thingies, we should better understand like what the rules actually are. So I'm going to do a little quiz with you. Those two variables here, f1 and f2, do they have the same type? No. They have different types because you wrote two different lambda expressions. And even though they're token for token the same, they are two different expressions, and therefore the compiler is going to generate a new closure type for each one. So there are going to be two different types. Okay, what about this one? Same type? Yes, this is the same type because you only wrote one lambda expression. So you only have one type, and then the second one, you're just copying it, right? So it's going to have the same type. What about this one? Same type? Yes. Again, because you only wrote one lambda expression. So I guess we're getting good at this. This is going to be easy. F1 and F2, is this the same type? Yes. What about this? Same type? No, because you have two different lambda expressions. And now it's a hard one. What about this? Are x1 and x2 the same type? Who thinks they're the same type? Okay, who thinks they're not the same type? Okay, you're good, yeah. They actually have different types, even though you only wrote one lambda expression. And the reason is that every time you create one of those x's, you're going to instantiate, it's going to be a new template instantiation. And because it's a default template parameter, it's going to evaluate that every time you instantiate a new instantiation. So it's going to be as if it was a new lambda, because it's going to look at it again every time it instantiates a new template instantiation. It's going to look at this lambda again. It's going to treat it as a new lambda. So this is really curious, and actually there is a new idiom here, the unique types generator, which I'm going to credit Chris Yushak with the invention of this, because the first time I saw this was his tweet here, where he just posted, "You can do this. It works. God bold link." And then, yeah, there were some replies. Then they said, "Oh, this is so cool. I'll still find an abuse for it." And Gaspar also said, "Yeah, I'm going to use that. That's amazing." And I was like, okay, this is cool, but what do you want to use it for? Like, serious question, I don't know. And then turns out, well, this is actually really useful whenever you need to stamp out different types really easily. Previously, we had this __ counter macro. We don't need that anymore. We have a very, very easy way to just generate new types. And Corentin here gave another example. So there are use cases for these things. And I think this is really, really cool. So you can now have objects that look like it's the same type. It's actually a new type every time around. And there are like really interesting use cases for this, apparently. So that's really cool. And now we're already done with C++20, which is the current standard. And we come to the new standard, C++23. And I'm just going to quickly rush through this because I'm running out of time. C++23 has a new feature called Deducing This. And if you want to know more about Deducing This, come to my keynote on Thursday, where I'm going to go into a lot more detail about how this works. But just very, very quick overview. You have this problem if you, sometimes you have to write basically overloads on whether or not an object is const or not const, or whether it's ref or like L value or R value, and you keep, you have to like write these different overloads because like all these versions, they have to return a different type depending on whether it's an L value, an R value, or const or non-const. But every one of these 4 overloads has the same body. It's the same code. You have to write it over and over again, right? So that's not good. It's quadruplication, right? And before C++23, we don't really have good options here. So we can quadruplicate the code. We can say, OK, we're going to have one of these members which is going to implement the behavior, and the other 3 are going to refer to it. But because the parameter types don't match and the return types don't match, we have to write these ugly casts. We can also move this into a private function and say this is going to be the implementation and the other 4 are going to refer to it. Also not great. And then finally, probably the most frequent thing is going to be that some people are just going to omit some of these 4 overloads. And then that's really bad because you're going to either lose const correctness or you're going to lose performance because you're going to make unnecessary copies in some scenarios, or you might lose both of those things. In C23, we don't have to do this stuff anymore because now we can template on the type of self. And we can let the compiler deduce this for us. And we have this new syntax where we write this in the beginning of the parameter declaration. And that makes this implicit first argument, which is the this pointer for a member function. We can make it explicit. And we can now also template on what the type of the this object is that this is a member function of. And then the compiler is going to deduce for us, is this an L value, is this an R value, is this const or non-const, and it's going to do that using the normal rules for function template argument deduction. And we don't have to do this ourselves anymore. So we don't have to write these 4 overloads. We can just write one function which is going to work in all scenarios. So this is really, really great. And one thing that this allows is it allows us to write recursive lambdas. And that is really, really, really cool. So here's an example. I'm just going to use factorial. I guess that's one of the canonical kind of recursive things that you can write. Obviously, don't actually implement factorial like this, but it's kind of a toy example. So you want to write factorial as a lambda. So I just wrote this in this naive way. We have a lambda, which is taking an integer. It's computing the factorial. And for the recursive thing, it just kind of calls itself inside, right? Is this going to compile? Who thinks yes? Who thinks no? OK, yeah, it's not going to compile because you cannot refer to the f from within its own initializer, right? You haven't created the variable yet, so you cannot refer to it from within itself. Right? So that doesn't work. We cannot name a lambda within its own body. We can cheat. We can make it a std function, and we can capture that function. Then we can refer to it. But it's not great because std function is tape erasure. There's like overhead in there. We're going to have indirections. We're going to have potentially an allocation, even if we create one of those objects. So we have overhead in time and space. It's not good. So one other thing we can do is we cannot name the lambda within itself, but we can template it on the function that it's going to be calling within itself, okay? And then we can pass itself to itself like this. And this is going to work, but obviously it's a little bit awkward because now we just don't get a normal function call because we always have to pass the lambda to itself before we pass the actual argument to it. And so this is a little bit convoluted and weird. But you probably know now where this is going. We can now just use deducing this. And by writing this in the beginning of the parameter declaration, we just say, well, just use the implicit first argument of any member function, which is the this pointer, and just deduce that and just use that. And that's going to work. So now we can just call the function normally. Because it's an implicit argument, we don't have to pass it. We just write f5. We just call it naturally like this. But then because you wrote this auto self, the compiler is going to be like, you want to have this implicit first parameter, which is the this pointer. Let's deduce what it is. Let's deduce the type. And now you can name this parameter. You can call it self. That's a good convention. That's what Python people use, right? So it must be good. And you can call it within itself, and now it just works. And you might think, well, maybe this is kind of a toy thing. You're like, why would this be useful? But actually, Ben Dean gave a really, really good talk here last year about deducing this. So it's just an hour of things you can do with this new deducing this feature in C++23. And he gave this one example, which I just want to reproduce here, and that's going to be the last thing for today. This was his example where you want to do tree traversal. You have a binary tree, right? It's a classic computer science problem. And we're going to implement it as a variant. Okay, so it's either every tree is either a leaf or a node, and it's kind of recursive. And then what you want to do is you want to traverse the tree recursively and count the number of leaves, right? So we can now use the already familiar lambda overload set pattern here. So this is something that we already talked about today. And then this is our overload set. We're going to say, well, do a visit on this variant, and we're going to have 2 lambdas here. One overload for the leaf. Obviously, if you want to count the leaves and it's a leaf, then it's 1. and then 1 for the node. And then if you have a node, you count the leaves by taking the left child and counting the leaves, and taking the right child and counting the leaves, so you're going to call it recursively. And the really cool thing here is that if you call this thing from within itself recursively using deducing this, because it's using the normal rules of function template argument deduction, it's going to deduce the fully derived type insofar as it is known at compile time, which in this case it is. So if you refer to self here, the self is not the lambda that's in the red box. The self is the fully derived type, which is the whole overload set, right? So we're going to call the whole thing. So this is truly like a recursive call of overload here. And so this is how we can count the leaves in the node. So this is a classic question that people ask in C++ job interviews. So next time somebody wants you to implement tree traversal, you can write it like this, and you can really impress your interviewer. Although I do recommend that you have a cutting-edge compiler, otherwise it's not going to compile. Right now, as far as I know, the only compiler that already supports deducing this is the Microsoft compiler. But hopefully, Clang and GCC are going to catch up soon, and then you can do all of this stuff on a lot more platforms. And this is all I have for today. Thank you very much. Do we have time for questions, or? Yeah,
Two quick ones.
Yeah, cool.
How many threads can simultaneously initialize different static variables?
Different static variables. You mean how many threads can initialize the same static variable? So if you're initializing a static variable, the standard guarantees that it's thread safe, and it's going to happen exactly once on one of the threads that are trying to do it, right? So you're going to get, the compiler is going to generate locks for you, and it's going to generate like a flag. Has this been initialized yet? Which is going to be probably like an atomic flag. So there's going to be one thread that gets to initialize it, and all the other threads don't get to initialize it. So it doesn't really matter how many threads there are. There is no limit as far as the C++ standard is concerned. Any other questions? OK, well, oh, there's one more here.
Hi. Can you put a immediately invoked lambda in the initializer in the init capture of another lambda?
I don't see why not. Yeah, sure, you can.
Two small questions. On the overload set, if you have two lambdas with the same type, will it call both, or can you not do that?
It will say that it's ambiguous, because you're going to have essentially the same operator paren twice in the same class.
OK.
So that's
Other
not going to
question
compile.
on the third trick, where you have the assign a static in the constructor to get called once.
Yeah.
Is there ever a time you'd want to do that over call once with a once flag?
Probably if you really care about the performance of this thing and you measure std call once and it's not performant enough, then you would do this. But hopefully you would wrap this into your own, your library call once, instead of just writing this like as a naked statement like this.
Thank you.
Hey, I actually had a question on that second point as well. If for the run once trick you declared the variable thread local instead of static, would it run once per thread, or does it not work like that?
Bro, I don't know. I think so. Yes, somebody says yes. OK. Oh, Daisy says yes. OK, Daisy says yes. Daisy knows the stuff. She taught me this technique, so I trust her. Yes, the answer is yes.
All right. Thanks to both of you.
All right. Thank you very much.
I go one. I'm here. Hi.
Oh, OK.
Fine.
I think we're over time. I'm not sure, but yeah,
Okay,
please
I'll
ask.
tell you later then.
No, I'm fine. I don't know if we are allowed to keep going.
I'm going to give you a comment, which I'll strategically pose as a question.
All right.
Did you know you can actually use variadic init capture in Lambda to re-implement tuple with like 1.6 compile time speed up compared to std2?
I did not know that, but I want to hear more. I'm going to be here all week. Let's talk about it.
Cool.
Thank you so much for the comment, Vittorio. All right. Thank you very much.